Hi, my name is Bill Kinney, and I'm a math professor at Bethel University in St. Paul, Minnesota. And in this video, I'm going to do a bunch of practice problems for the Gateway exam for Calculus 2 on integration at Bethel, but certainly there will be practice problems that will be useful for your integration gateway at your school here. When you do integration gateways, it's a bunch of memorization and also a bunch of just skill with certain techniques. So there's memorized integrals to do. And the techniques include substitution, integration by parts, partial fractions, and knowing trigonometric identities in certain situations, okay? You're not going to get much out of this unless you've done some of that already, okay? If you've done all those kinds of techniques, that's when you're going to benefit most from this video. By the way, if you're looking for a derivative gateway, I did make a derivative gateway. I'll put the link to that in the upper right corner, practice problems for that, if you're interested in that. So again, what are gateways about? Gateway exams are meant to be, well, first of all, done without calculators, so you're using things that are in your own mind. You're memorizing things because we think it's important to develop mastery, or what you might call accuracy, and fluency. Are you getting things exactly right? There's typically no partial credit on gateways, and you got to either get 100% right or maybe 1 or 2 wrong at most. And are you developing fluency? Can you do things quickly? Because you practice them so much that you don't have to think about it too long. But definitely integration gateways are harder than derivative gateways. So you definitely need to practice these things more. So let's go ahead and start here. There are 12 problems total. Not quite sure how long this is going to take me, but I'll go as quick as I can while giving some explanation. But again, you should practice ahead of time before you watch this video. So the first integral to do is the integral of 1 over 2x plus 3 dx. And the first thing that should come to your mind when you look at this is similar to the integral of 1 over x dx. Okay, instead of an x in the bottom, we've got a 2x plus 3. And that integral is a memorized integral. And, well, x could be positive or negative here. You want your answer to be defined for positive or negative values of x. You should memorize that it's a logarithm, natural logarithm, not just of x, but of the absolute value of x. That'll allow this antiderivative to be defined for negative values of x as well. You do need to check that it really works for those negative values of x, but it does. Then don't forget your plus c when you're doing an indefinite integral like this, a pure antiderivative. There's no definite integrals on Bethel's gateway. There could be on your gateway, and then you'd have to use the fundamental theorem of calculus. Okay, so it's similar to that. We want to use that in some way. That's the idea. So how? Well, why not just call this something else, this 2x plus 3? Give it a new name. Define a new variable, typically called u, to equal 2x plus 3. That's why this is sometimes called u substitution. Now, there's nothing special about the letter u. It's just a common thing to use. However, if you do that, oops, sorry, move there. If you do that, the answer is not going to be the natural log of the absolute value of u plus c. Okay? It's related to that, but it's not equal to that. You've got to find how du depends on dx. Now, you can do this by just differentiating u with respect to x and then writing a dx there to the right, and I will usually do that. However, initially you might want to think of it as what's the derivative of u with respect to x? In this case, u equals 2x plus 3, so the derivative with respect to x is 2. And then pretend this is a fraction and quote-unquote multiply both sides by dx. Now, when we teach you this Leibniz notation for the derivative, most teachers typically emphasize that this is not a fraction. It's the derivative, the rate of change of u with respect to x. But it doesn't hurt to pretend it's a fraction in a lot of situations. And in fact, that's how the original creators of calculus thought of it. Leibniz in particular, that's why it's called Leibniz notation. So you don't just do the integral of 1 over u du. You do the integral of 1 over u, replace the dx with 1/2 du. Dividing both sides of this by 2, 1/2 du would be dx. 1 over u times 1/2 du. So there's an extra factor of 1/2 that comes in. And that, being a constant that's being multiplied, can just stay there. You can write 1/2 times the natural log of the absolute value of u plus c. But you're not done. You want to get things back in terms of x here. Now replace u with 2x plus 3. Don't forget your absolute value signs. Technically, this is true on the domain where we're not dividing by 0 here, so x cannot be, what would it be, negative 3/2. That's the only value x where this does not work here. Okay, so we want the absolute value signs there to make our domain as big as possible to match the domain of the original integrand. And again, don't forget your plus c with these indefinite integrals, these pure antiderivatives. You can always check, or almost always check your answers on these things, at least if you remember your derivative rules. I can differentiate this with respect to x, ddx. I have to use the chain rule. Okay? And in fact, anytime you use a substitution like this, when you do the checking, you have to use the chain rule because substitution is kind of the reverse of the chain rule. We have an inner function that's 2x plus 3. I'm going to need to multiply times the derivative of that inner function after I go ahead and differentiate. By the way, there's no absolute value signs that you should put here. Okay, the absolute value signs are only there. Don't forget, again, to multiply times the derivative of the inner function. Chain rule says take the derivative of the outside function, which is 1/2 times the natural log of the absolute value of something. Then plug in the inner function, which is 2x plus 3, then multiply times the derivative of the inner function. The 2's cancel here, leaving you with the original integrand, 1 over 2x plus 3. So it does work, okay? That matches, you can't see it now, but this is 1 over 2x plus 3 right there. All right, again, there's 12 problems total, varying degrees of difficulty. Here's the second one. This involves memorization, and, well, you could do it without a substitution, but maybe to be careful, I'll go ahead and do it with a substitution. First of all, you've got the integral of the sum of two things. Integrals are linear, linearity property, just like derivatives are. The integral of a sum is the sum of the integrals. It's a little funny with indefinite integrals because at the end you always just tack on the plus c, but don't worry about it. So we can write this as the integral of 6x dx plus the integral of secant squared 5x dx. That first integral should be easy for you, right? This is just the reverse of the power rule. You have to, instead of subtracting 1 from the exponent, you have to add 1 to it. And instead of multiplying times that exponent, you have to divide by it, or divide by 1 plus what the current exponent is. In other words, the answer is 6 times x squared over 2. We took the exponent of 1, added 1 to it to get 2, and divide by that same number. And this simplifies to 3x squared, and you can always check right away. The derivative of that is 6x. You can always check. What about this one, though? That looks hard, doesn't it? Okay, it's a memorized one with a substitution if we want to be careful. Let's go ahead and be careful. Let's use a substitution. If this were just a u instead of a 5x, then we would be integrating secant squared of u, which is a memorized integral. It's tangent of u plus c. So go ahead and let u be the 5x. But just like before, you've got to get du in terms of dx. And maybe if you prefer dx in terms of du, dx is going to be 1/5 du. So the dx does not just get replaced by du, it gets replaced by, in this case, 1/5 du. And that 1/5 needs to be there. And again, it's because it's the reverse of the chain rule. Also, in the end, after you integrate with respect to u, you need to go back to x. That's the original variable. So again, the integral of secant squared is a memorized integral. It's tangent. It's not the final answer. Replace u with 5x. Again, you can always check. Just do it in my mind this time. Again, the derivative of 3x squared, bring down the 2, you get 6x to the first power. Same thing as that. Differentiate this, the 1/5 will stay there, the derivative of tangent of 5x, you need the chain rule for, you're going to get secant squared of 5x times 5, times the derivative of the inside function. The 5 and the 1/5 will cancel, leaving you with a secant squared of 5x. Okay? I just checked it in my mind there. If you didn't quite follow that, you might want to pause the video and write that down. Write down your own checking. This one we have an integral of a sum and difference of a bunch of terms, each of which is actually fairly easy to integrate. This is fairly easy to integrate. You can do a substitution. I think this time I'll just do it by guessing. With simple substitutions, you can often do it by guessing instead. This one is memorized because, well, x to the negative 1 is the same as 1 over x. You're going to get a natural logarithm. This one's easier than it looks. Square root of x is the same as x to the 1/2 power. X to the 4th times x to the 1/2, you have to add the exponents to get x to the 4.5 power, which is the same as x to the 9/2 power. I don't mark it wrong if my students write 4.5 because yes, 4.5 does equal 9/2, but I think it's better to practice with fractions. That looks complicated, but it's a memorized integral. The integral of that is the inverse sine function, or arcsine function. And with these two, well, with this one, you can use the reverse of the power rule, again, adding 1 to the exponent and dividing by that same number. Let's do this one, again, by guessing, okay? I know the derivative of e to the x is e to the x, and the integral, therefore, of e to the x is e to the x plus c. I've got a 2 in front, the 2 just stays there. I've got a 3x instead of an x. The answer's got to involve e to the 3x. Leave a little space with some constant in front of it. What should the constant be? Some people are better at this kind of thing than others. If it was just this, if that were the answer, we'd see we're wrong, because when we check this, we'd get e to the 3x times 3, not times 2. So I need something in front of it such that when I multiply by 3, I get 2. Hey, 2/3. That's something that when multiplied by 3 gives me 2. When you differentiate this and get an extra factor of 3 from the chain rule, the 3's will cancel, you'll get 2. So I did that by guessing. And again, some people are pretty good at that. Some people are not so good, okay? If you're not so good at guessing like that, then go ahead and use a substitution for this part. U equals 3x. D would be 3 dx. Dx would be 1/3 du. 1/3 times 2 is 2/3. That's where the 2/3 would come from. Integral of 1 over x is the natural log of the absolute value of x. You want your domain to be as big as possible, the same domain as this thing. Although, it's a little funny here, technically speaking, this thing is only defined in calculus 1 at least for x greater than or equal to 0. So I'm sort of already implicitly assuming x is positive anyway for this whole function. And in fact, even less than 1. So we're not dividing by 0 there, and we don't have the square root of a negative number there. We're really implicitly assuming x is strictly between 0 and 1 here. But it doesn't hurt to put the absolute value signs, so go ahead and do it just to play it safe. Now here, add 1 to the exponents. 9/2 plus 1 is 11/2. Divide by that same number, or multiply by its reciprocal. This is the same as 2/11 x to the 11/2, and 11/2 is 5.5, and that would be fine for my students to write that. But here's where the benefit of fractions goes. 2/11, if you write it as a decimal, is a repeating decimal. It's not so pleasant to write. This is a better way to write it, really. Okay? And then finally, again, this one's a memorized one. You can write it as arcsine x, and then don't forget your plus c, or inverse sine of x. Okay, these symbols mean the same thing. They're the inverse of the sine function when you restrict the domain of the sine function to it's negative pi over 2 to positive pi over 2 in radians. Either notation is okay. I think this notation is better personally than that notation, because this makes you think it's the same as 1 over sine of x, but it's not. 1 over sine of x would be the cosecant function, and those are different. So this notation is probably better because of that, but you'll see both notations used. So the answer is essentially here, though this could be replaced by that, and this could be replaced by that. As far as checking goes, there's really not much to check because it's based on memorized things. I mean, you may want to check this one when you bring down the 11 halves. 11 halves times 2 11ths is 1. And then you get 9 halves there, just like that. We already checked this one. You get an extra factor of 3 when you differentiate. The 3's will cancel, leaving you with a 2. Okay? On to problem number 4. This one's based on memorized stuff as well, but maybe a little trickier, especially with this part right there. Integral of e to the negative 4x. Okay, you can try it by substitution, but if you're good at guessing, you're going to get negative 1/4 e to the negative 4x. Again, you can always check. If you're afraid you're making a mistake in your guessing, check it. That. Differentiate it. You're going to get an extra factor of negative 4 when you use the chain rule. Negative 4 times negative 1/4 is positive 1. Just like there's a coefficient of positive 1, even though you don't see it written. This one, well, you could do a substitution. You could let u equal 2x here, but you don't need to. 1 over 2x is indeed the same as 1/2 times 1 over x. So you get a natural logarithm with a 1/2 in front of it. So you don't have to do a substitution. I mean, you can also just guess as well. You're going to get plus 1/2 natural log of the absolute value of x. Once again, we want our domain to be as big as possible here. For real x, we're never dividing by 0 there, so we don't need to worry. X can't be 0 there, but it can be negative. What about this one? That one looks hard. It is based on a memorized integral. You should memorize this one, that the integral of 1 over 1 plus x squared dx is arctangent of x plus c. Or this could be written as inverse tangent. Like that. Either way is okay. Again, these mean the same thing. This does not mean 1 over tangent because that would be cotangent. Those are different. Don't forget your plus c. But we have a 4 there instead of a 4x squared instead of a 1 times x squared. So should we do a substitution? Should we guess? I would recommend using a substitution, but you got to be careful still. You want to think of this thing as 2x quantity squared and let u equal 2x instead of like 4x or something like that. That's the way you want to do it here. So that when I do that u substitution, I end up getting 1 over 1 plus u squared. That's the reason I did it that way. Let u equal 2x. So du is going to be 2 dx, and dx is going to be 1/2 du. So you get an extra 1/2, which I can put in front of the integral. I'll go ahead and do that. 1/2 in front of the integral. 1 over 1 plus u squared. Because I let u equal 2x, as opposed to, say, 4x or something. If fraction there becomes 1 over 1 plus u squared. That's what I want so that I can relate it to this. Almost done here. So rewrite what I have up there. Negative 1/4 e to the negative 4x plus 1/2 natural log of the absolute value of x plus 1/2 arctangent of u, but I'll go ahead and replace u with 2x here, plus c. If we check this, Here we get an extra factor of -4 from the chain rule, which would cancel with the -1/4 to get +1 times e to the -4x. That works. Here we're going to get 1/2 times 1/x, which is the same as 1/2x. When you differentiate this, let's do that in blue, this one right here, you got a 1/2, 1/1 plus 2x quantity squared times 2 from the chain rule. Those 2's cancel. This 2x quantity squared becomes 4x squared. Okay? This is the answer here. On to number 5. This one looks difficult, but it's actually pretty easy. Here, our substitution, u, that we're going to use is not a linear function of x. Okay, it's a little tricky to realize this. If I let u be x to the 5th, then I'd have an e to the u there. And e to the u, du, is an easy integral to do. But what do I do about the x to the 4th there? Well, I still need to find du in terms of dx. Differentiate u with respect to x to get 5x to the 4th. Quote unquote, multiply both sides by dx. Put the dx over there. We're almost to the point where we can do the right thing here. Instead of dividing both sides by 5x to the 4th here to get dx in terms of du, it's better to just divide both sides by 5 to write 1/5 du as equal to x to the 4th dx. Because now this times this can be replaced with 1/5 du. And I just realized here that I'm using blue now still. I meant to go back to red. Okay, that'll be 1/5 du. That can be replaced by that. And I'll bring the 1/5 in front of you. 1/5 times the integral e to the u du. And now that integral is easy to do. 1/5 e to the u plus c, but get back in terms of x, you're going to get 1/5 e to the x to the 5th plus c. And if you check that with the chain rule, now I'll do my checking in red. You get 1/5 e to the x to the 5th times the derivative of x to the 5th, that's the inside function. Sorry about that. It's 5 there. Times the derivative of x to the 5th, which is 5x to the 4th. 5's cancel, leaving you with e x to the 5th times x to the 4th, same as the original integrand. Okay? So it does work. You know, if that were not an x to the 4th, if it were an x to the 3rd, or x squared, or x to the 6th, or x to the 5th, it'd be less clear if this method would work. Might still, but you might have to do other things as well. Okay, so the fact that this is an x to the 5th and this is an x to the 4th made this work. This one's kind of similar, except I purposely put an extra factor of 7 in the integrand. And it also involves a trig function. Integral of cosine is something to memorize. But once again, let u be the higher power of x. In this case, x to the 4th. And again, it's fortunate that this power of x is 1 lower. Du will be 4x cubed dx. I differentiate u with respect to x and put that extra dx there. It's a 7x cubed dx here and here. Whereas we have a 4 there. What should I do? How about multiplying both sides of this by a constant that would cancel with the 4 to give me a 7? Multiply both sides by 7/4. 7/4 du would be 7x cubed dx. So I can replace the 7x cubed dx with 7 fourths du. And I can bring the 7 fourths out in front of the integral. And I'm going to get a cosine of u du. Careful here, it's tricky. What's the integral of cosine of u? Is it positive or negative sine of u? It's positive. The derivative of cosine of u with respect to u would be negative sine of u. But the integral of cosine is sine, because the derivative of sine of u is cosine of u. Okay? All these tricky things. You got to get this exactly right, so it's a challenging thing for people. Again, most gateway exams, your teacher should give you more than one chance to pass, a certain number of retakes, although it's not necessarily the same problems in the retake. There we go, let's check it. Once again, we've used substitution. When we check, we'll use the chain rule. The derivative of sine is cosine. So the derivative of the outside function is the cosine here. Plug in the inside function times the derivative of the inside function. The 4's will cancel. You'll be left with 7x cubed cosine x to the 4th, same as the original function. Okay? So this is working. Okay? I mean, you could make a mistake in your checking. That would be a problem. But I'm pretty sure everything is right here so far. On to number 7. And now we end up needing a new technique. You could try a substitution here. You could try u equals 2x. Or maybe u equals 3x plus 5. It's not going to be as helpful as you would want. It's not that it gives you a wrong integral, a new integral, but it's not an easier integral to do. We need another technique. We need something called integration by parts. Integration by parts, which again, if you're watching this video, this is something you should know already. Most typically written as the integral of u dv is u times v minus the integral of v du. If you want to be a little bit more formal about this, this is kind of an informal way to write it. You could maybe say it as integral of u of x v prime of x dx. This thing really represents the dv equals u of x times v of x minus the integral of v of x times u prime of x dx. This is really the du. Here, it's implicit that there's another variable like x that we're not showing. So this is a less formal way of writing it. This is more formal. This comes from the product rule. Integration by parts is the reverse of the product rule. And you can kind of see that here with the changing of the derivative on whether it's on the first or second function here and here. If you rearrange this, you can end up seeing that this follows from the product rule. But even if you know the formula, it doesn't mean you can apply it very well, at least not in all circumstances. It tends to be the most common situation that people use it when you have something involving powers of x, a polynomial in x, in this case a linear function of x, maybe a quadratic function of x, maybe a cubic, times maybe a cosine or sine of something or an e to something. That's like the most common situation where people end up using integration by parts, and that is the situation here. And in that situation, it's best to let u be the 3x plus 5, and dv, or v prime, be the sine of 2x. If you think of it as dv, you'd want to add on the extra dx. If you do it that way, it does make the integral possible to do, because what happens is you end up getting a u prime to be something simpler, 3 in this case, and this integral over here ends up being easier to do. Let's go ahead and do that here. So I'm going to let u be the 3x plus 5. Differentiate that with respect to x, that's going to mean du is 3 dx. U prime of x is 3. That's another way to think of that. And pick, so that's what this is. That's u. Let this thing with a dx in there be your dv. dv is going to be sine of 2x dx. So what is v that I'm going to need here in this formula, here and here? What I'm really saying here is v prime of x is sine of 2x. V is an integral of sine of 2x. Antiderivative. Technically speaking, I need substitution to do that integral, but it's simple enough that you can guess if you're careful. Careful here, integral of sine is negative cosine, because the derivative of cosine is negative sine. You're going to get negative, because of the 2 there, you're going to get a 1/2 cosine of 2x. Do you need a plus c? No. You just need one antiderivative. You might as well take c to be 0. Now use the formula. U of x times v of x, or just u times v for shorthand. The product of these two things comes first. That'll be negative 1/2 in parentheses 3x plus 5 times the cosine of 2x. I just multiplied these two things. There's a negative sign there. Minus, there's a minus here, not a plus, minus the integral of v du. This times this. And you go back to x's, by the way. You stay with the x's. It's not like substitution where you stay with u. Product of these things. 3 times negative 1/2 is negative 3/2. I can bring that in front of the integral. And then these two minus signs become a plus plus. I already took care of the 3 and the negative 1/2. I just have a cosine of 2x in here. And then the final answer, which I think I will write in blue, is negative 1/2 3x plus 5. You can certainly multiply the negative 1/2 through there to get negative 3/2 x minus 5/2, but then you need that in parentheses because you're multiplying that whole thing by cosine of 2x. I still need to do this integral. Integral of cosine is sine. I'm going to get another factor of 1/2. 3/2 times 1/2 is 3/4 sine 2x plus c. There's your final answer if I have not made a mistake. I think I need to check this. Let's go ahead and erase these formulas to give me room to check it. Check it. Do that in green. I need the product rule on the derivative of this part. Again, the integration by parts is the reverse of the product rule. So think of this as the first function, negative 1/2 times 3x plus 5, and cosine 2x as the second function. The derivative of the first is going to be negative 3/2. Right, multiply the negative 1/2 through there if you like. And then times the second function. Oh, stop that. Don't know why it does that. It's all in how I press, but I'm not used to smart words really. And then the first function times the derivative of the second. The derivative of cosine is negative sine. That's going to cancel with the negative sign there to give a plus. And you're also going to get a factor of 2 from the chain rule there. We needed the chain rule because we needed substitution in doing that part there. These 2's cancel. And then, hope I haven't made a mistake, the derivative of that one, I get a cosine, I'm going to also get an extra factor of 2. I'm going to get plus 3/2 cosine of 2x, right? 3/2 instead of 3/4 because of the extra factor of 2. And yeah, this cancels completely with that. And here this simplifies to just this times this, 3x plus 5 times the sine of 2x. There we go, that's the original integrand. Wow, okay, I was afraid I was going to make a mistake there. So that's good. On to number 8. Again, there's 12 problems total. Once again, you might try a substitution first, u equals maybe x to the 5th, but you quickly realize that's not so helpful. Then you say, okay, how about integration by parts? But what should I let u be and what should I let dv be? You could try letting u equal x to the 5th, because then du is going to be 5x to the 4th dx. That's a lower power of x, and that sounds helpful. But the problem with that is if you let dv be natural log of x dx, you've got to find v by integrating natural log. That's not so easy. It is possible to do, but you'd actually need integration by parts for that as well. It's better to do what's a little counterintuitive here. Let u actually be the natural log of x, and let dv be x to the 5th dx. That's actually the better thing to do here. It takes a little bit of experimentation, or your teacher telling you, like I'm telling you now. There's this acronym, I think it's called LIATE. It's not something I typically memorize it, but I guess I have sort of memorized it here. Log, inverse, arc, trig, exponential is sort of the order of priority in letting u equal whatever you have here. If you got a logarithm or an inverse function like a natural logarithm, okay, natural logarithm, or a arcsine or arccosine, but that's what the A stands for. I'm a little confused about what the LIATE meant. That's what you want to order of priority as far as what to let u be in many situations when you've got those functions. Not guaranteed to work always. And in fact, like in the last problem, I let u equal 3x plus 5, and that's a more common kind of problem actually. Find du and find v. To find du, I need to differentiate this. That's easy. That's 1 over x dx. To find v, I need to integrate x to the 5th. That's not so hard. 1/6 x to the 6th. Plus c, but the c can be taken to be 0. The integral is going to be uv minus the integral of v du. Product of these two things is 1/6 x to the 6th times natural log of x. Notice I'm not using absolute value signs here. And that is because the domain of this is implicitly positive x. So I don't need absolute value signs here. It's assumed x is positive here. But I guess it doesn't hurt to put absolute value signs there. Minus the integral of v du, the product of these two things. One of the x's cancels, so you end up integrating 1/6 x to the 5th dx when you multiply these two things. Okay, that is correct. And that's fairly easy to do. So we get 1/6 x to the 6th natural log of x minus add 1 to the exponent to get a 6, and then divide by another 6. You're going to get 1/36 x to the 6th plus c. Checking. Notice in checking this part, you need the product rule. The derivative of 1/6 x to the 6th is x to the 5th times the second function plus the first function times the derivative of the second. That x will cancel with one of these to give you a 5 there. Minus the derivative of 1/36 x to the 6th is minus, bring the 6 down to get 6/36 or 1/6. Subtract 1 from the exponent, x to the 5th. And it's going to be these two things that cancel. leaving you with that, which is the same as the original integrand. Take a breath. I know this is kind of a long video because integration is definitely harder than differentiation. Oh, and I didn't make it easy on myself for this one. This one ends up being kind of a pain, but it's worth doing. Okay, you need to do some difficult ones sometimes. Once again, if you think about Liate, whether you think of it in terms of inverse function or arc function, you want to let u be the arctangent one, not x. Because if u were x, d would be dx, but dv would be arctangent of x dx, and you'd have to use integration by parts to find v. That sounds bad. And I mean, that is possible, but it's still not really helpful. Let dv be x dx. Then du, oh, I guess I'm back to blue here. It's 1 over 1 plus x squared dx, right? Derivative of arctangent of x, which again is the same as the inverse tangent. And v, I need to integrate this to get 1/2 x squared. Okay? By the way, if this were just a 1 instead of an x, you'd be integrating arctangent. You'd still use integration by parts with u equal to arctangent of x, and dv would be just dx, and v would be just an x in that case. And that integral ends up being easier to do than this one will be. This one we're also going to have to use some long division of polynomials, which sounds unpleasant, but it's not too bad in this situation. Okay, integration by parts, u times v. Let me go ahead and write it again. uv minus the integral of v du. U times v is the product of these two things. 1/2 x squared arctangent of x. So the answer is still involves an arctangent. Minus the integral of v du. I'll bring the 1/2 in front and get an x squared over. Let me write the bottom in the opposite way. As x squared plus 1 instead of 1 plus x squared. It's certainly okay to do that. It's more traditional when you're integrating or when you're differentiating arctangent to write it this way, but you certainly can switch it around. I'm doing it for a reason, and that reason is related to now long division. I've got a rational function here where the degree of the top and the bottom are the same. Anytime that happens, or if the degree of the top is higher than the degree of the bottom, degree meaning the highest power, you want to use long division of polynomials first before trying to integrate. So we need to take x squared and divide by x squared plus 1. Like this. How do you do that? Well, what do you need to multiply this highest power here, x squared, by to get this thing here, x squared? You need to multiply it by 1. 1 times x squared is x squared. Put that 1 up there. Multiply that 1 times this here to get x squared plus 1. Then remember, with long division you subtract. The x squareds cancel. 0 minus 1 is -1. Once you're to the point where you can no longer say, hey, what do I need to multiply x squared by to get this, and still get an expression that is x to the 0 power or higher, you're done. Actually, this is the remainder in the division. This is the quotient in the division, and this is the remainder. The remainder has got to have a lower degree, in this case 0, than what you're dividing by, in this case 2. It could have involved x, that's possible, but here it just is a constant. And what this means is that this fraction here, x squared over x squared plus 1, is the quotient 1 plus the remainder over the original thing you were dividing by, plus -1 over x squared plus 1. If you don't believe that, check it, okay? Add by getting a common denominator of x squared plus 1. This is the same as 1 is the same as x squared plus 1 over x squared plus 1. And with the second fraction, now you just have the minus 1 there. Those cancel, leaving you with x squared over x squared plus 1. It does work, okay? And the point is, this is now much easier to think about integrating than this is. That's the purpose. Integrating that's pretty easy. It's going to be x minus arctangent x. We already have a minus sign there too, so I need to be careful. Looks like the final answer, which I'll put in red, is 1/2 x squared arctangent x minus 1/2 times the integral of 1 minus 1/2 x minus 1/2 times the integral of negative 1 over x squared plus 1. It's going to be plus 1/2 arctangent of x. Don't forget your plus c. Oh yeah, that was tricky. Differentiate, use the product rule here. Derivative of 1/2 x squared is just x. That's the derivative of the first function times the second function plus the first function, 1/2 x squared, times the derivative of the second, which is 1 over, no, I'll write it as 1 plus x squared. It's just the more traditional way to do it, I guess. That's the derivative of this thing. Then the derivative of this is minus 1/2. It's not clear that this is going to work out, but I hope it does. Derivative of this is going to be 1/2 times 1 over 1 plus x squared. Is this definitely going to work out? We want the answer to be x times arctangent of x. We want all this stuff to cancel. Get a common denominator. That's the way to go. And hopefully the numerator will completely cancel. The denominator is going to be 2 times 1 plus x squared. Think about that. The denominator here. You already have a 2 there and 1 plus x squared. You already have a 2 there. You already have a 2 times 1 plus x squared there. Here, the 2's already down in the bottom, so I just have an x squared. Here, with a minus 1, I really need to multiply this negative 1/2 times 1 plus x squared over 1 plus x squared. So I'm really going to subtract 1 and also subtract x squared. And with this one, you have plus 1. Yeah, x squareds cancel, 1's cancel. You're left with 0 there. It goes away. The final answer for the derivative in the checking is x times arctangent of x. Same as the original Land-Grant. Wow. Okay? I get worried that I'm making mistakes too, so if you feel the same way, you know that your professors sometimes feel that way too. This one is a partial fractions problem. If you practice partial fractions, you should be able to recognize it that way. You have a rational function that you're integrating right at the start, and the degree of the top is less than the degree of the bottom. And the bottom is already nicely factored for you. If it were not factored, you'd have to try to factor it yourself. And if you FOIL this out, this is the same as, well, negative x squared is going to be the x squared term. The x term is going to be a 4x minus 3x. It's just an x. And the constant term is going to be 3 times 4 is 12. That's what the bottom would be if you did not factor it. You can factor it this way. You could also write this as x minus 4 and bring a negative sign in front as well. Or you can bring the negative, factor a negative 1 out of this as well right from the start. But it is factored for us. And again, it's a rational function where the degree of the top, which is 1, the highest power of x, is less than the degree of the bottom, which is 2. It's quadratic. And if that's the case, if you've got 2 linear factors in the bottom, which is the simplest kind of case, you want to write this combined fraction as the sum of two fractions with these two different denominators here, sort of reversing the process of fraction addition. And the goal here is to solve for a and b. You want to solve for the constants a and b that will make these two things equal for all x in the domain of this function, which would be all x excluding -3 and +4. However, the trick I'm about to show you will involve plugging in x equals -3 and +4 after multiplying both sides of this by x plus 3 times 4 minus x. Let's do that multiplication in blue here. Now, that might seem a little fishy. Why would the trick work? I don't want to fully explain it here other than just to show you it works. You get complete cancellation on the left, and when you use the distributive property, you get partial cancellation on the right. The left simplifies to just 2x. The right simplifies to what? Multiply the x plus 3's cancel with this first term, leaving you with a times 4 minus x. And the 4 minus x is canceled with this next one, leaving you with b times x plus 3. Technically speaking, that computation is only valid when x is not -3 or 4. When x is not -3 and x is not equal to 4. But now I'm going to solve for a and b. I'm going to plug in those numbers for x, -3 and 4. And I will get a and b pretty quickly. And the proof is in the pudding, so to speak. In the checking, it does work. Okay, you might scratch your head and wonder why it works. I don't want to get into why it works. Just appreciate the fact that it works. Plug in those special values of x, like 4. Now, some people teach this as set up a system of equations by equating like terms, constant terms, and x terms, and that's fine, but this is quicker, okay? We're after our answer as quick as we can here. It doesn't always work out so nicely as in this example, but in Bethel's gateway exam, it will always work out like this, at least. I'm not sure if it will on yours. If I plug in x equals 4 there, I get 0. This goes away. Plug in x equals 4 here, I get 7b. 4 plus 3, 7. So b is 8/7. If I plug in x equals -3, that's going to make the b term go away, and I'm going to be able to solve for a. -3 there, 2 times -3 is -6. 4 minus -3 is 4 plus 3. I get a 7 there as well. And the b term goes away. So a can be solved for now. A is going to be -6/7. I'm not going to take the time to do it, but you can check if you replace a here with -6/7 and b with 8/7 and add the fractions by getting a common denominator, you will get 2x. Actually, maybe I should check that because essentially that's going to be the check of my final answer as well. Let's go ahead and check that. Let's do it in green. -6/7 over x plus 3 plus 8/7 over 4 minus x. Get a common denominator of x plus 3 times 4 minus x. So you're going to get, with the first one here, you need to multiply the top and bottom by 4 minus x. And with the second one, you need to multiply the top and the bottom by x plus 3. On the bottom, you'll have the product, x plus 3 times 4 minus x, as you should. Now simplify the top end. The constant term should go away, and the x term should simplify to 2x. Does it? I'll just sort of do it above here. -6/7 times 4 is -24/7. -6/7 times -x is positive 6/7x. Then we have a positive 8/7x. And then 8/7 times 3 is 24/7. Wow. Yeah, those cancel. These two combine to give you 14/7x, which is 2x. It works. And essentially, when I check the final answer, which I haven't done any integration yet, but when I do the integration, checking the final answer, essentially I'm checking by getting it to this point, and then this algebra helps me check that it matches the original thing. Let's go back to red now. So what do we have here? This fraction here, 2x over x plus 3 times 4 minus x, is equal to this thing here. Integrate the whole fraction by integrating each of these and adding the results. I'll bring the negative 6/7 out in front first. 1 over x plus 3 dx, and then a plus 8/7 out in front. Integral of 1 over 4 minus x dx. One more thing to be careful about here. You can do these with substitution. Here let u equal x plus 3. Here let u equal 4 minus x. If you do so, and don't forget absolute value signs in this situation, because we want the domain of the answer to be the same as the domain of the original, you're going to get negative 6/7 natural log of x, the absolute value of x plus 3. With the second one, though, because of the minus sign there, you're going to get a minus sign here. If you do let u equal 4 minus x, then du will be negative dx. Get a negative sign. That's a common place people make a mistake. Technically speaking, by properties of logarithms, you can also combine those things, but pretty likely you might make a mistake if you do that, so I would not. At Bethel, we would be fine with leaving it like this instead of trying to write it as the log of one thing plus c. There's properties of logs that would allow you to combine those, but you might make a mistake if you do so. So leave it like that. We're almost done. 2 more problems. They are trigonometric integrals. That can be done with some special techniques, trigonometric identities. Both of these last 2 problems are the product of powers of cosine and sine. Now, when you do such an integral, you really hope at least one of those powers is odd, because it makes the problem a lot easier. If they're both even, then the problem's harder. It can be much harder, in fact. The last problem, number 12, they're both going to be even, but they're going to be relatively low even numbers, 2 in fact, for both the power of cosine and sine. That's a little tricky, but it's definitely doable and not too long a time. Here we have the product of powers of cosine and sine, and the cosine one is odd. That's good. You have one of those being odd. First thing you want to do is you want to pull off one of those factors. Think of cosine to the 5th of x as cosine to the 4th of x times cosine of x. And bring that one factor next to the dx. Like this. Okay, that's the first thing to do. We're going to use a substitution now. U equals something. Not integration by parts. You want to let u be chosen to either be sine of x or cosine of x. Choose it so that this thing right there is the du. Okay, which means u better be sine of x in this problem. Now, if the sine had had odd power, if this had been cosine to the 4th of x times sine to the 5th of x, I'd pull off one of the factors of sine and I get sine of x dx there. That would be my du, or at least negative du. U would be cosine of x, but then du would be negative sine of x dx. I'd have to worry about an extra minus sign. Okay, practice that. Okay, after I do this one, practice that one. So u is going to be sine of x. Du is therefore cosine of x dx. That's going to be your du. This is going to be u to the fourth. But what about that thing? Does that somehow got to get pulled into the du? What do I do with that? You need what should be everybody's favorite trigonometric identity, the most commonly used, cosine squared of x plus sine squared of x equals 1. This thing right here is the same as cos squared x quantity squared, and that is the same as 1 minus sine squared x quantity squared. Since cos squared x plus sine squared x equals 1, that means cos squared x equals 1 minus sine squared x. And now this is 1 minus u squared quantity squared. This whole thing is 1 minus u squared quantity squared, which I will go ahead and multiply out here. This is just algebra before doing my integral. This is 1 minus u squared times itself. I'd have to FOIL. First times first will be 1 times 1, which is 1. Outside times outside and inside times inside are both negative u squared. Combine them, I get negative 2u squared. Last times last is negative u squared times itself is positive u to the fourth. Don't forget to multiply by u to the fourth. Write that u to the fourth right there. So I'm going to get integral of u to the fourth minus 2u to the sixth plus u to the eighth du. And that's an integral that's easy to do because that's a polynomial. Right? Hopefully I've not made a mistake. Just looking over things here, I think this all looks good. Gives you 1/5 u to the fifth minus 2/7 u to the seventh plus 1/9 u to the ninth plus c. Now replace u with sine of x. The final answer is 1/5 sine of x to the fifth, which is traditionally written like this, minus 2/7 sine of x to the seventh, which is traditionally written like this, plus 1/9 sine of x to the ninth, which is traditionally written like this, then plus c. That is correct if I have not made any mistakes, and I'll check this after I finish making the video, and it won't get posted on YouTube unless it's all right, so I guess you can assume it's all right. Checking it would be a bit of a pain. Yeah. I mean, in differentiating each of these, you're going to need the chain rule, and in each case, you're going to get an extra factor of the derivative of sine of x, which is cosine of x, which is where that comes from. But to fully check it, you'd have to then factor. You'd have to sort of reverse what we did here. It's probably not worth checking by differentiation. It's probably just worth double checking all your work here. Okay. This, by the way, is not the only way the answer can be written because there's so many, hundreds or thousands of trigonometric identities out there. You might see the answer in a textbook or a book of integrals, or using a computer program like Mathematica. You might see the answer written differently. If you type this into Wolfram Alpha, you might see the answer written differently. But that doesn't mean it's not the same answer, okay? Because of trigonometric identities, functions that look different could in fact be the same. On to the last problem, number 12. Here we have it, the product of two powers of cosine and sine where both powers are even. If I made one of those powers 4 or 6 or both of them 8, it would be a monstrous problem. You would not want to do it by hand. But make them both 2, it's doable. And once again, you need trigonometric identities, I think is sort of the best way to do it. But they're not the same trigonometric identities. It's not cos squared x plus sine squared x equals 1, though it's related to that. Cos squared x can be written, it turns out, as 1/2 plus 1/2 cosine 2x. That's a memorized identity. That's not quite as common as the other one from the previous problem. It is true you should check it with your calculator. Graph both of these functions, you'll get the same graph. If you graph just this one, you'll get something that's lower than this one, but matching its oscillations by a vertical shift of 1/2. Plug in numbers, you get the same values. This is true. It's an identity. It's not an equation to solve. It's equal for all x, no matter what x is. There's a similar one for sine squared x, but it doesn't involve the sine. It still involves the cosine. It's 1/2 minus 1/2 cos 2x. That is true. And again, you can check that by plugging numbers in or graphing or whatever. Do notice if you add these two equations, you get cos squared x plus sine squared x equals 1. 1/2 plus 1/2 is 1, and these cancel. So it at least jives with that, though it doesn't prove that these are right. Okay? So this is what to use. Initially, you are going to need to do this multiplication now. FOIL. First times first, 1/2 times 1/2 is 1/4. Outside times outside is 1/4 cos 2x. Inside, or minus 1/4. Inside times inside is positive 1/4 cos 2x. Those will cancel in this case. Last times last is 1/4 cos squared 4x. Or 2x, sorry. Getting ahead of myself. 1/4 is easy to integrate, but what about 1/4 cos squared 2x? You need this identity again. This is true no matter what x is. So it's also true if the input is of the form 2x. But you have to make an adjustment on the right side as well. Replace x with 2x. There you'll get cosine of 4x. These two identities really mean the same thing. Another identity would be cosine squared 3x would be 1/2 plus 1/2 cos 6x. Both of these are true no matter what x is. Graphically, going from x to 2x corresponds to a horizontal compression by a factor of 2 of the graphs. So that's what to use here. We get 1/4 x, first of all, when we integrate that one, minus 1/4 times the integral of 1/2 plus 1/2 cos 4x, and now that's going to be an integral that's not too hard to do. Technically, you could say use a substitution, u equals 4x, but you should practice doing it in your head as well. Here we have a 1/4 times 1/2 is 1/8, and we have a minus sign. When we integrate that, we'll get minus 1/8 x. 1/4 x minus 1/8 x is going to be 1/8 x. 1/4 minus 1/8 is 1/8. And then we have a minus 1/4 times 1/2 is 1/8, but then when we integrate cos 4x, we'll get another factor of 1/4. We're going to get minus 1/32. Integral of cosine is sine. Should I say that again? Minus 1/4 times 1/2 is negative 1/8. But then when I integrate cos 4x, I'll get another factor of 1/4. 1/8 times 1/4 is 1/32. Integrate cosine, get a sine 4x. If you want to do it with the substitution, u would be 4x, du would be 4dx, dx would be 1/4 du. This is correct. If you tried to check it by differentiation, you kind of have to work backwards in some way, and it would not be super easy. Okay, this would be hard to check. So, I believe this is right. Again, I'll check it after I finish making the video, before I post it. Thank you so much for watching.